Good morning, everyone. So, recall that in the last class we have introduced the concept of recurrence relation, and we have seen that how to write down the recurrence relation in case of one variable. We will see some questions based on one variable. At the same time, we will see some questions based on the two variables. To start with, let us consider the following case. So a man visits a general store every day where he buys either one of two types of chocolates costing $1 or one of three types of chocolate costing $2. So there are only two choices, either he spent $1 or he spent $2. If he spent $1, then the remaining amount can be spent in an minus 1 ways, and if he spent $2, then the remaining amount would be spent in three ways. Yes, so this is the remaining amount can be spent in an minus 2 ways, and there are three ways for spending $2 and two ways for spending $1. That's why my required an is 2 an minus 1 plus 3 an minus 2, where a naught is equal to 1, which means if he do not spend, or he spent $0 only one way, he do not buy anything, and a1 is equal to 2, which means if he spend $1, then there are two types of the chocolate, so there are two ways of spending $1. Yes, so in the previous question you have seen that the coefficients of an, or the successive terms an minus 1, an minus 2, was always 1. This is the case where you can see that the coefficients were other than 1. So now consider the two variable. So let a and k denote the number of ways to select a subset of k objects from a set of n distinct objects. Find a recurrence relation for a and k. So if you have to find the recurrence relation, in this particular case you can see that a and k is same as c and k. Yes, and we have done a recurrence relation for c and k, which is cn minus 1k plus cn minus 1k minus 1. Yes, and how did it? When we have to select a subset of k objects, or we have to form a committee with k people out of n people, we say that either a person p is in the committee or is not in the committee, and based on these two cases we got c and k as cn minus 1k plus cn minus 1k minus 1, which can be written as a n k, a n minus 1k plus a n minus 1k minus 1. Yes, and the same thing we know that cn0 is equal to 1, so a n0 and cnn is equal to 1 for n greater than equal to 0. Now again you can observe here is that what is a and 0. So the number of ways to select a subset of 0 object from a set of n object, or which is same as spending $0. So here also you can see that mathematically we always assume it to be equal to 1. Because of this we could have the other relations for the c and k. Find a recurrence relation for the ways to distribute n identical word is important, into k distinct boxes with 2 to 4 balls in each box. We did the same problem using the generating function, and generating function is simply x square plus x cube plus x raised to the power 4. Yes, now we have to write down the recurrence relation, and there are two variables, one is n balls and the other is k boxes. Yes, so a and k is the number of the ways to distribute n balls into k boxes. Now what we do is that we put, there are three cases we can make. We put 2 balls in a box, 3 balls in a box, or 4 balls in a box. Yes, so when we are putting 2 in a box, we are not identifying or choosing one box out of k boxes, we are just saying in any box. and that's why it can be done in only one way. So if you put two balls in a box, then we distribute the remaining n minus 2 balls in k minus 1 boxes. If you put 3, then n minus 3 in k minus 1, and if you put 4, then n minus 4 k minus 1, with the initial condition a21, a31 and a41 is equal to 1, which means the number of the ways of putting these two balls in any one of the box, putting 3 balls in any one of the box, or putting 4 balls in any one of the box. And any one means just which comes first, we just put it, we do not select the box. And for the other one, an1 is equal to g. Yes, the other problem says that repeat the problem with balls of 3 colors. So now earlier they were identical balls, but in the second case now balls are of 3 colors. It means they are not identical. So for the first one it was very easy to write down the generating function, but for the second case it's not trivial. But you will realize that writing the recurrence relation is not at all difficult. Yes, so now a and k is again number of ways to distribute n balls into k boxes, provided balls are of 3 colors. So when the balls are of 3 colors, so when you put 2 balls, then there are many choices. For example, the colors are red, green and black. So either it is red green, red black, green black, so different combinations are there. So now recall that I have to choose 2 balls out of these 3 balls, and these 3 balls are distinct. So the formula was C r plus n minus 1 and r. Yes, so I have to choose 2 balls out of 3, and in that case once I choose 2, then I distribute the remaining a n minus 2 in k n minus 1. Similarly, if I choose 3 out of 3, so it is a n minus 3 k n minus 1, and the last one is c 4 plus 3 minus 1 and 4, and a n minus 4 k minus 1. Yes, initial conditions again you can write down the same. A21 is 6 because this value is 6, A31 is 10, and A41 is 15. Okay, let's see the next question now. Find the recurrence relation for the number of n digit ternary sequences. So ternary means sequences made up of 0, 1, 2 with even number of zeros. So we'll use the same approach, either you start with 1 or you start with 0. When you start with 1, there are remaining n minus 1 positions. If you fill these n minus 1 positions in a n minus 1 ways, then overall there are even zeros, because these n minus 1 positions have even zeros, and along with 1 it remains even zeros. In case of 1, if you choose a n minus 1, then this has even zeros, and overall it becomes odd zeros, which we do not require. It means the better option is, here I should take odd zeros so that overall I have even zeros. So this is the better choice. Now for doing this, what should I do is, when you think of a ternary sequences, you can break it into 2 sets. So one is with odd number of zeros, one is with even number of the zeros, and their union would give you the total number of the ternary sequence. So if I have to find the number of the ternary sequences of length n minus 1 with odd number of the zeros, then what I do, I consider the total number of the sequence, which is 3 raised to the power n minus 1, because each position has 3 choices, 0, 1 or 2, minus the sequence with even number of the zeros, number of the sequences of length n minus 1 with even number of the zeros. that gives me the number of the sequences with odd zeros, and when I combine it with 0, because initially it's 0, so first position 0, in total I will get even number of the zeros. Yes, so therefore either I start with 2 or 1, I will get an minus 1 plus an minus 1 in both the cases, and in the last case I get 3n minus 1 minus an minus 1. Yes, now you may also argue that to obtain the recurrence relation, in case of 2 and 1 you will use the same approach, but in case of the 0, what you do is that you fix a 0, and then in the remaining position you add one more 0. Yes, which can be added in cn minus 1 comma 1 ways. So cn minus 1 comma 1 ways. Now it ensures that there are even number of the zeros, and the remaining n minus 2 positions now you fill with the even number of the zeros. Yes. Now is this recurrence relation correct or not? Please think over it and you will realize that it is not correct. I will tell you why. So let's say you start with the 0, then A, then 0, then B. So here you choose 0 at the third position. In the other case you choose 0 at the second position. In both the cases, if I take A is equal to B is equal to 0, then both are giving me the same solution. It means there is a repetition of the solutions. I am not missing any solution, that you can verify, but the solutions get repeated, and that's why this recurrence relation is not correct. The next one is find recurrence relation for the number of ternary sequences of length n with even number of zeros and even number of ones. So now it's more complex. So one thing which you can observe here is that when we say even number of zeros and even number of the ones, so like in the previous case when I did 3 raised to the power n minus 1 minus a n minus 1, I found odd number of the zeros, or I found sequence of length n minus 1 with odd number of the zeros. So here again I need the following cases: when odd 0 and even ones, or when even 1 and odd 0 and the odd 0 and odd 1. Yes, so I can denote it. So let an, which is the required with even zeros even ones, bn is even zeros odd ones, and cn is odd zeros even ones. I am not considering odd zeros and odd ones because it can be easily observed that out of the total sequences, which is 3 raised to the power n, I can subtract an, bn and cn. That gives me number of n digit ternary sequences with odd zeros and odd ones. So that's easy to address. Now let's say that I want to find first an. So when I have to find the an, so what are the possible choices? It starts with, I need, so it start with 1, or it start with 0, it start with 2. When it start with 2, then you choose an minus 1 ways. Yes, even number of the zeros, even number of the ones. When it start with 1, then you need odd ones and even zeros. Yes, this I took as bn minus 1. When it start with 0, I need even ones and odd zeros. This is cn minus 1. Therefore an is an minus 1 plus bn minus 1 plus cn minus 1. Now I cannot solve this recurrence relation because bn and cn are unknown. So it means I need the recurrence relation for bn and cn as well, which would be in the same way. So your bn is, you need even O's, even zeros and odd ones. Yes, so if you start with 2, not a problem, it will give you bn minus 1. If you start with 1, then you need even zeros and even ones, which is an minus 1. And if you start with 0, then you need odd zeros and odd ones. So odd 0, odd ones means 3 raised to the power n minus 1 minus an minus 1 minus bn minus 1 minus cn minus 1. Yes, so that gives you bn as, if you simplify it, 3 raised to the power n minus 1 minus cn minus 1, and similarly you get cn. Now you have the recurrence relation for an, bn and cn. So using all of them, you can compute an while simultaneously computing bn and cn. Okay, so in the next class we will see that how do we solve the recurrence relations.